An isometric scaling, there's not a good definition out there, but it's when the original length measurements obey, or it's when the measurements obey the algebraic equation y is equal to some constant alpha times x. And I should have used alpha all the way through, and you're going to see that I'm going to apologize in advance. I didn't. I did the mathematical thing and used different letters to mean the same things. So apologies at the beginning. So this measurement could be x equals area, which would be, you would expect it to, you'd have area on the right side, but it's directly proportional to whatever other measurement you have. And so it has to obey and be governed by this equation. So if you have a square with side length L, then what we do know is this square has area L squared. Now, if I stretch that square by a factor of s, then the new area is going to be s squared times L squared. So we really have that area is directly proportional to L squared. So the measurement of area is going to be directly proportional to this other area, which is our other measurement, which is L squared. And likewise, volume is going to be directly proportional to L cubed. It's just a stretch of the original shape. So linear scaling in L resulted in a linear scaling of all other measurements. And that's isometric. That's what is meant by isometric scaling. A couple other ways to say it, that is stretching each side by a constant amount resulted in a direct proportional stretch of the area and volume. And specifically, another way we could say this is that the new area is directly proportional to the old by a factor of alpha squared in this case, and the new volume is directly proportional to the old volume by a factor of alpha cubed. And I believe I used s's to begin with, so s squared and s cubed, not alphas. Now, if we don't have that, we can make an assumption. So say volume's not going to be alpha times L to the cube power. We're making an assumption that that's not the case. That means that we're still assuming there's some kind of power relationship, that this is the functional form between volume and length. That's an assumption, and I do think that we should say that in the discussion, that we're assuming this functional form, and I'll kind of hit that one more time. Allometry doesn't have a good definition on the internet, but it means different measure. That's the actual meaning. And there does not appear to be a good definition, rigorous definition. But the best definition is a model that does not assume that sizes or measures of size increase proportionally to length. So it's not going to be size is going to be alpha to the length of what it should be if it was just linear, length to the cubed if it was volume, and length to the square if it was area. So when we assume such a power law relationship, we're really allowing for functional forms of this type. Size is equal alpha to the length beta, where beta is not what we expected it to be. But that doesn't mean that you can't assume it to be some other functional form. So we're making this assumption that this is the relationship. It could have been size is equal to alpha times natural log of length. So I do think we should be clear that the assumption is that weight is equal to alpha times h to the b, that we're assuming that functional form. And we would expect weight, which is directly proportional to volume by density, we would expect that beta to be cubed if it was a isometry, and it's not. It's squared, which is surprising. So that's what it tells you, that the actual weight per meter of height is going to be different for tall people versus short people. It's not what we would expect it to be. So I hope that makes better sense. And I think we should have the paper say this as clearly as we can.